All right, folks, I'm excited for a couple reasons about this lesson. First of all, it represents the last bit of new learning for the unit on optimization, so that's always exciting when we reach the end of a unit. Second of all, I'm excited because I think of all of the content that we've done so far this year, this lesson has the most practical implications for real life learning or real life applications that you might encounter. All right, so let's go ahead, let's jump in and let's talk about cost. Oh, money, that's a fun topic, always. All right, and number one, we're talking about a box without a top. This box has a square base, and this box is made or constructed using 2 square meters of sheet metal. They want us to, in part A, express the volume of the box as a function of its base width, which they want us to call x. So I'm going to go ahead and start by drawing a sketch of this box with the square base. And they tell us in the question that this width of the base has a length of x, so I'll go ahead and label that in my picture. And because the base is in the shape of a square, I know that if one of the dimensions of that square are x, then the other one must be x also. And for lack of something better, I'm going to go ahead and call the height of my box h. They come right out in the problem and tell us they want us to work with volume. What they don't come right out and tell us is that the other formula we're going to be working with here is going to be surface area. How do I know surface area? Well, we've constructed this box using the 2 square meters. Constructing the box would be the left side, the right side, the front, the back, the bottom, and that is another name for surface area. So those are the two formulas that we're going to be working with here in this question. I'm going to go ahead and write them both down. It doesn't matter which one you put where, but just like it has been since the beginning of time, formula for this box and its volume is going to be V equals length times width times height. Formula for the surface area here. Ordinarily, I would have both a top and a bottom, but they tell me in this question that we are working without a top for our box, so I'm going to have only the bottom, plus the two rectangles that make up the left sides and right sides of this box, plus the two rectangles that form the front sides and the back sides. So I don't think it really matters here which of these two formulas you start with. I'm going to go ahead and start with volume. Volume is going to be length times width times height. So my length and width here are x and x. My height is h. So in simplest form, I've got x squared h. That's as far as I can take that volume formula at this time. So I'm going to go instead and work with my surface area. I know that this box is constructed using those 2 square meters. So I know that my surface area is 2. Going on now to fill in the other variables in the formula. Well, my base is this square whose sides or whose dimensions are x by x. So the area of that square base is going to be x squared. The rectangles that make up the left side and the right side of my box measure x units long by h units high. So each of those will have an area of x times h. And the two rectangles that make up the left front side and the back side of my box, well, they have a length of x and a width of h, so they too have an area of x times h. I'm going to go simplify the terms on the right side of this equation now. So 2 times the quantity xh is just 2xh, and the same thing for that last term. I've got a couple terms here that are like terms, so I'm going to go combine them. This is where some of you struggled in class. Make sure you remember your rules for combining like terms from 8th and 9th grade. Remember, when you combine like terms, we combine the coefficients, but keep the rest the same. So combining 2xh plus 2xh is going to give us 4 of those xh's. At this point, I'm not really sure what I'm supposed to solve for, the x or the h. So I'm going to go back and reread the question. This tells me I'm looking to do volume in terms of x. So I want to express this volume using only the variable x. So that h is going to be kind of my problem child. My at h is going to be what I'm going to need to get rid of. I'm going to accomplish that by going back over here to the surface area and solving that for h. So I'm trying to isolate the h or undo all of the algebra that has been done to h. You might say get the h by itself. So I'm going to start by subtracting x squared from both sides. To undo multiplying the h by the 4x, I'm going to divide both sides by the 4x. So I end up with each h is equal to 2 minus x squared over 4x. It's ugly, it's not beautiful, but it is what it is. I'm going to take that value of h now, the 2 minus x squared over 4x, and I'm going to go over here to my volume formula, and I'm going to replace that h with the 2 minus x squared over 4x. So now in my volume formula, I'm multiplying two fractions. I'm going to go ahead and simplify this by multiplying numerators to numerators. So 2x squared minus x to the fourth all over 4x. To make this simpler and easier, I should have simplified before I multiplied. I didn't do that. I can simplify at the end, but I probably should have taken out or removed here an x from the numerator and an x from the denominator. And again, that would have made my mission a little bit easier. But I'm just going to continue on with what I have. I'm going to factor out an x squared from each of the terms in the numerator. And again, you're seeing I'm kind of undoing some of the math I've done here. Now I can remove an x. And what I end up with at the end of the day, volume is equal to x times 2 minus x over 4. I think that should be a 2 minus x squared. All right, so moral of the story there, it's easier to simplify at the beginning than it is to simplify at the end. But if you do what I did, and don't simplify until the end, you'll still end up with the same answer. All right, part B says what value of x is going to maximize this volume? So what side length is going to give us the greatest volume for the box? So I'm seeing maximize in that problem, and I'm thinking max on the computer, so or max in the calculator. So I'm going to go ahead and take that function y equals x times 2 minus x squared over 4, and I'm going to go dump that into my calculator. Let's see, we need a graph, not a calculator. We're going to need a calculator eventually, but we need the graph first. This is where, too, you want to be putting things into the calculator exactly as I'm putting things into the calculator, making sure that you know how to put things into the calculator and that it's not going to kick back or resist. If you're going to encounter a problem, we want you to encounter that problem now rather than when you get to an assessment. All right, so there's my function. Not super helpful the way that we've drawn it. I'm going to say that if we're looking for here volume, our y represents volume. I only care about volume that's positive. I only care about side lengths that are positive. So I'm going to look on my positive x-axis and my positive y-axis, and I'm going to go adjust these guys here so that I'm only looking at the positive x-axis So I might make this -1 just so I can still see my origin and the positive y-axis. So it looks like I only need to go up as far as 1 there. And I'm going to change this, make this -1. All right, that gives me a not perfect, but a much better picture um, than what I started with. I want the maximum. So the maximum would be the highest point on that graph. The way that I'm going to find it is to go into the menu, analyze the graph, and look for the maximum value. So boom and boom. You want to make sure your settings are set so that you can see all of these decimal places. So I'm going to say my maximum happens at the point whose coordinates are, and it looks like it says round to 2 decimal places, so 0.82 and 0.27 for y. And this is where you have to remember what the variable x represents and what the variable y represents. X, remember, represents a side of our square. So this is the side of the square. Y, well, when we put this function into the calculator, y was representative of our volume. So side of the square is 0.82, value of x, or sorry, the volume is 0.27. This question is asking for the value of x. So 0.82. And I'm going to say centimeters because they tell, sorry, meters. If this had asked what was the maximum volume of the box that can be made, well, then I would have answered with the y value, the 0.27 cubic meters. So just be a good, careful reader and make sure you're asking or giving whatever it is that has been requested of you in the question. All right, I think that about takes care of everything for number 1. Good times, fun times. All right, number 2. This is the volume of a cylindrical can, and they tell us that that volume is 1,000 cubic meters. The cost of materials for the top and the bottom of the can is 75 cents a square centimeter. Material for the lateral surface area is 50 cents per square centimeter. Find the cost of the can in terms of its radius. Find the dimensions of the least expensive can. So again, I'm thinking about this question and I'm thinking somebody sitting somewhere at the Coca-Cola plant is trying to minimize the amount of aluminum that they need to use to make their cans, thereby making the cost to produce their Coca-Cola even cheaper. So again, practical, real-life application. The geometry teacher in me gets super excited here because, again, a lot of geometric implications as well. So this can is in the shape of a cylinder. Like the boxes, I'm terrible at drawing cylinders, so I'm just going to start with a circle and a circle for the bases of my can, and then I connect my circle, therefore making a nice little cylinder. Like the box, we are talking about this in terms of volume because they give us here volume, and we're talking about surface area. So these are the two formulas that we're going to need. So volume of a cylinder from my formula sheet is volume is equal to pi times r times h. And the surface area, they don't come right out and tell us that this can has a top, but I'm going to say it does because I'm trying to envision a Coca-Cola can without a top or a can of green beans without a top. Doesn't happen. So surface area for this cylinder is going to be 2 pi r squared plus 2 pi rh. And it's really important that you understand where the pieces of the surface area came from. So I'm going to talk a little bit about that 2 pi r squared plus the 2 pi rh because that's going to be essential later in our problem. Pi r squared, you may or may not remember from your geometry class, hopefully you do, or even from middle school. Pi r squared is the formula for finding the area of the circle. So when we talk 2 pi r squared, we're really talking about finding the areas of those circular bases. That's where that comes from in the formula. So when we talk about 2 pi r squared, that's the area of the two circular bases. This 2 pi rh at the end, that's going to be the area that makes up the curved sides of our can. If you want to think about the curved pieces being the sides. That's going to be super important later on in the problem when we go talk about costs and money. So again, you need to know where that formula comes from and what those pieces represent in that formula. All right, I don't care whether we go do surface area first or volume first. What do they tell us about the dimensions in this can? They tell us that the radius is r. For lack of something better, I'm going to call the height h. Our goal here is to find the cost. So again, that kind of adds a new element here to what it is that we're doing. I'm going to go ahead and I'm going to start working with the volume because they tell me in this problem that the volume is 1,000 square centimeters. So I'm going to go plug that in there. 1,000 equals pi times r squared times h. What they don't tell me here is they don't tell me what variable to use to represent the surface area. So I don't know if I want to do the surface area in terms of r or the surface area in terms of h. Well, this is where I'm going to go back over to this formula right here. And I'm going to say, is it easier to solve this formula for h, or is it easier to solve this formula for r? Well, if I solve that formula for r, it's going to involve doing some square roots somewhere. I don't want to have to do that. So I'm going to go ahead and I'm going to solve this for h by dividing both sides by pi r squared. So doing that tells me that each h is 1,000 divided by pi r squared. Again, it's not wrong to solve for r, but it's just way harder. So I'm going to go now and I'm going to express my surface area in terms of h. Sorry, in terms of r. I'm going to replace each h with an r. So in terms of its radius, the surface area is 2 pi r squared. No problems, nothing that has to be replaced in that first term. But in my second term now, I've got to replace that h with its equivalent 1,000 divided by pi r squared. So the 2 stays, the pi stays, the r stays, but the h, and I used a hard bracket there for no reason. If you want to use parentheses, parentheses are fine. 1,000 divided by pi r squared. Before I think about cost, I'm going to simplify this expression completely. So the first term, fine, no problems. The second term, though, I'm not going to make the same mistake I made in the first problem. I'm going to simplify before I multiply. So I've got a pi that's a factor in both the numerator and denominator. I can cancel those out. I've got an r that's a factor in both the numerator and denominator, so I'll remove one from the numerator and one from the denominator. So it looks like when I simplify the second piece of this formula, I've got 2,000 in the numerator, and I've got 1 times r, or r, in the denominator. So that's my surface area in terms of the radius. Notice I'm very clear and specific about how I express what it is I'm working with. I'm telling the reader, I'm telling you, this is surface area in terms of the radius. Going back to what it asked us in the question though, and it wants us to find the cost. So we need to think about the cost of these materials that are going to make up our surface area. I'm now going to change my surface area to a C because I'm talking about cost in terms of the radius. Well, what do they tell us about the cost in the problem? They tell us in the problem that the cost for the top and bottom, so that would be the circular bases, is 75 cents per square centimeter. So what I'm going to do is I'm going to take this area that made up my circular bases, the top and bottom, and I'm going to multiply it by the cost. So I'm going to multiply that 0.75, the amount per square centimeter, times the 2 pi r squared, the number of square centimeters I have in my circles. Then I'm going to take the cost of the material for the sides. Well, the cost of the material for the sides, or fancy geometric name for that is lateral surface area, that's 50 cents per square centimeter. So I'm going to take that cost, 0.50, and multiply it times the area of my lateral surfaces, or my area of my curved pieces that make up the sides of my can. 2,000 divided by r. Perfect. So again, note here that the surface area function changed into the cost function simply by multiplying the cost of each piece by how much square units I have for each of those pieces. And again, I'm going to now go simplify. Super, super, super important that you simplify this. So I'm going to multiply 0.75 times 2 on my calculator. That'll give me 1.5 pi r squared for the simplified cost of the circular bases. And I'll put that over 1. Half of 2,000 is 1,000 for my new numerator. 1 times r is r for my new denominator. Oh, I'm loving this. Awesome. So we have this cost now in terms of the radius. Now's the time when I'm going to go plug this into my calculator. So the function I'm going to plug into my calculator is going to be y equals 1.5 x squared plus 1,000 divided by x. All right, let's dig the calculator out. Let me go home and open up a new document. So the pi button, remember, is down in the bottom left corner of your calculator. Me being me, I'm always going to take a minute to make sure that I plug this into the calculator correctly, because if I didn't, that's going to mess everything up. Voila, hit enter. Ooh, and it almost appears as though I'm getting a whole lot of nothing here. All right, so I'm going to remember again that in this question, I'm working with lengths and areas, and I want all of these things to be positive. So I'm going to go play games with my viewing window. I really don't care about the negative x-axis, and I really don't care about the negative x-axis. So I'm going to go change both of those to -1. I like to go bigger rather than smaller, so I just changed the positive y-axis to 1,000. You can't see it because it's slightly off the screen, but I'm not even going to go play games with a positive x-axis because I've already got a nice window that I can use now to go figure out what I need to find. Want to point out to you here that what we're looking for here is the least expensive. So least expensive would be the minimum cost. So when I go to my calculator here, I'm looking for the smallest or the minimum value. So again, I'm going in to analyze the graph. I think I hit a wrong button there, so let me try this again. Analyze the graph, choice 2, minimum, boom, boom. So I'm going to say from my graph, the minimum value appears at the point whose coordinates are, so they want nearest tenth. I'm going to round this to 4.7, comma 316.8. And again, this is my x, this is my y. And if I go back to this formula, x was my radius. The y in my formula represented the cost. So to answer the question, this question wanted us to find the dimensions. So the dimensions are going to be the radius and the height. So the radius that will produce the least expensive can is going to be that 4.7 centimeters. Notice that the height is not anywhere here in our ordered pair. So that's a problem. We have to go find the height. We're going to use this formula right here that we had to find height. I'm going to say we're going to do this in the calculator, and we're going to use the full calculator display for R. And you can do this a couple different ways. You can either type everything all out. I'm going to do a little bit of copy and paste. So just like I would on the computer, the shortcut for copying on the calculator is Control C. So I'm going to highlight that and I'm going to hit Control C. I'm going to go open up a new document. This time I want to do a calculator. And to find that H value, I want to take 1,000 and I want to divide it by pi. And just like I would on the computer, I'm going to Control V to paste to the second. If you don't want to do Control paste, then just copy or just write all those decimals down. Make sure you plug them into the calculator, but make sure that when you go to find the height, you use the full calculator display on your calculator. So my calculator here is telling me 14.2. And again, if you don't use the full calculator display, your height will be wrong due to early rounding in the problem. All right, so the dimensions that will produce the least expensive can, we have found. If it asked what was the cost of the least expensive can, your cost would be $316.80 something cents. Whew, good stuff. All right, I know I'm long on the video, guys, but I want to keep going and look at one more example with you. This one also is a box. Like the first example, this one too has a square base. So I'm going to go ahead and jump right in. I'll try to talk a little faster. I don't want to talk so fast that we lose something in translation though, and I say something that doesn't make sense. So there's my square box. I'm going to tell x and x, it's square, so they both have to have the same measure, h for the height. We're talking again volume and surface area. So we're back to those same formulas. We do have a top this time, so that's going to affect our surface area a little bit. Not our volume, but our surface area. Volume is still length times width times height. Surface area is going to be 2 of those top and bottoms, plus 2 of those rectangles that make up the left and right, plus 2 of those rectangles that make up the front and back. Doesn't matter which formula you do first. So my volume is x squared h. They want us to now do surface area in terms of one variable. I'm going to go ahead and plug in 1,000 for the volume, which I probably should have done a little bit earlier, but doesn't matter as long as it gets done. My surface area here, the top and bottoms are each x squared. The left and right are each xh. The front and back are each xh. So my surface area here, 2x squared plus 2xh plus 2xh, or in other words, 2x squared plus 4xh. All right, so now I'm at the point where I need to express the surface area in terms of just one variable. I'm going to go back over here to my volume formula. It's going to be much easier to solve that formula for h than for x. So I'm going to go ahead and solve for h. And I'm going to go back over here now, and I'm going to express this only in terms of x. So the 2x squared, fine, not a problem. But the h, I need to replace with 1,000 divided by x squared. So this was a 4x times 1,000 over x squared. And again, I'm going to simplify. So in terms of x, my surface area is 2x squared. I'm going to be smart and work smarter and not harder and remove a factor of x from both the numerator and denominator before I multiply. Remember, you can do that after, it just ends up being more work. So in terms of one variable, x, our surface area of this square box is 2x squared plus 4,000 divided by x. Domain, I'm not going to talk too much about this, but I'm going to say the surface area has to be a positive number. So domain for the surface area going to be 0 to infinity. That goes along the same idea with what I talked about a little bit in the last problem, where because these variables represent something out there in the real world, we can't have negative surface area, we can't have negative length, and that's why we're only concerned about the positive x-axis and the positive y-axis when we go to put these things in our calculator. Letter C says find the dimensions of the box with the smallest surface area. So smallest would be the minimum. So I'm going to go ahead and plug this into my calculator and find its minimum. I think just in the interest of time, I'm going to tell you that when I plug this into my calculator, I found the minimum point to have coordinates 10, 600. And again, I'll remind you that this is x and this is y. And in our problem, x represents a side of the square. And y represented our surface area. And dimensions, when we talk about dimensions, we're talking about length, width, and height. So the dimensions of this box that are going to minimize the surface area, well, I've got 10 for each of the x's. I also need to find that height. So the height I'm going to find by going back here. H we said is 1,000 divided by x squared. And again, when I plug this into my calculator, I'm going to use the full calculator display. In this case, it's not an issue because it came out to be a whole number, but in the event that it didn't, I would want to make sure I use the full calculator display to find that. When I plug into my calculator, I find that the height is also 10. So 1,000 divided by 100, or 10 squared, equals 10. All right, in letter D, it says, suppose that the material for the base and the top of the box is $5 per square centimeter, and the material for the sides are $3 per square centimeter. Write an expression that represents the costs of the materials for this box. Well, this is where we have to remember where things came from in our formula. The 2x squared represents the surface area of our top and bottom. This 4,000x came from the four sides. So when I go to find cost here now, I'm going to multiply the cost of the top and bottom by this 2x squared, multiply the cost of the materials for the sides by this 4,000 over x. So cost, now in terms of x, so notice that I've changed that to cost. $5 per square centimeter, so 5 times the area of the top and bottom. Well, area of the top and bottom is 2x squared, plus $3 a square centimeter for the sides. The sides are 4,000 divided by x. So in simplest form now, our cost in terms of x is 10x squared plus 12,000 divided by x. And if we wanted to, we could plug that into the calculator, find the side lengths that would determine the minimum cost, figure out the actual minimum cost. But I know I'm running way long on time here. I want to thank you, thank you, thank you for all of you who have paid attention through here to the end. Um, Mr. Korea has your homework, so you're good to go there. Hopefully, I'll be back with you tomorrow and we will all be back together, one big happy family again. All right, again, thanks, guys. My deepest appreciation for watching all the way through to the end.